All right. 6.2 through 6.4. It goes really quick. Now, first thing I want to say is the on the homeworks, when you're typing in the reasons, like on some proofs and things, and I'm sorry about this, but it's really the way it's got to be. When you're entering those theorems from chapter 6, the big, long theorems, you got to type them out. Now, I believe you can shorten them just a bit. For example, if it says, like the one that says, if a quadrilateral is a parallelogram, then pairs of opposite sides are congruent. You could just type this, I think. Try it and see. I think you can just say, if parallelogram, then opposite sides are congruent. You don't have to say if a quadrilateral. I think you can just say if parallelogram, or later on in the chapter, if rhombus, whatever. So you don't have to say, you can shorten it a bit. But it's still, I understand it's kind of a lot of stuff to enter, but think of it as typing practice, I guess. I don't know. Okay, so 6.2. This one, I looked in there. I noticed a lot of you guys have done some good work on this, so there's already a pretty good start on this. But let's take a look. Okay, what we want to do in this one, in 6.2, we're talking about parallelograms. Definition of a parallelogram is exactly what it sounds like, and we all pretty much know this. Parallelogram is a quadrilateral where both pairs of opposite sides are parallel. Okay, that's the definition of a parallelogram. If we've got a parallelogram, then there are a bunch of things we know about it, important properties of parallelograms. And these are those 4 theorems that pop up in 7.2. First one says, if we've got a parallelogram, then we know for a fact that both pairs of opposite sides are congruent. Okay, that's important. That's very useful, important to know. So there's one theorem. We also know that if we have a parallelogram, both pairs of opposite angles are congruent. Okay? And we know what else, if you can remember. We got those 2. What other ones do we know?
That smallest angle, same as smallest angle.
Okay, that in a triangle, that's true. Okay, consecutive angles. Any consecutive angles in a parallelogram are supplementary. There's another one. Okay, so for example, angle P and S would be supplementary. Their measures would add to 180. But so would P and Q, so would Q and R, so would R and S. Any combination of 2 consecutive angles, their measures have to add to 180. And then the last one. Remember that one? Opposite sides are congruent, opposite angles are congruent, consecutive angles are supplementary. What was the 4th one for parallelograms? Had to do with diagonals. Was it diagonals? Bisect each other. Yeah, there's the 4th one. If it's a parallelogram, then guaranteed the diagonals of that parallelogram bisect each other. So they cut each other into 2 congruent pieces. Okay? All right, so the things we do with that then is, we can answer the kinds of stuff you're going to be doing in the homework that uses those properties. Things like this. If you're given a parallelogram like this, and you're told that the length of side FG is 5, then what's the length of side JH? 5, yeah, because it's parallelogram, so they're congruent. Okay. What's the length of JK? 3, because we know that the diagonals bisect each other, and so that's got to be the midpoint of both of those diagonals, right? So if that's 3, that's 3. Okay, good. What about this one? This is a parallelogram. PQRS is a parallelogram. So if we're told that the measure of angle P is 70, we really could find all the other angles. What would the measure of angle R be?
70.
70, because they're congruent. Good, so let's fill these in. And what about the measure of angle Q?
110, because there's something.
Yeah, we know these have to add to 180, right? So 180 minus 70 would be 110. If we wanted to, we could fill that one in too. Okay? All right, so let's look at a little proof. PQRS is a parallelogram. Well, not really a proof, sorry. Let's find the value of x here. So what could we do? Now, just don't say it out loud. Everybody take a look at this for a second. See if you can come up with a strategy. We want to find the value of x. What's the, oh, don't say anything yet. Think in your mind here, what's the relationship? I got to be able to use a geometry relationship to come up with some equation if I'm going to solve for x.
Plus 3x.
120 plus 3x.
Yeah. Okay. So we know 3x plus 120 is 180. So then the algebra would be pretty simple. What are the steps in order we go through to solve for x?
120 on both sides.
Good.
Dividing both sides by 2.
Very good. And we get x equals 20. Good. Okay? No problem there. All right. So what about this guy? Let's do a little proof. Okay, so given that A, B, C, D, now look at that one. A, B, C, D, that's that top kind of wide parallelogram. That's a parallelogram, we're told that. And also A, E, F, G. So we get this guy right here that's also a parallelogram. We want to prove that angles 1 and 3 are congruent. Okay? Any suggestions how maybe we could do that? Raise your hand if you can think of a way we could start with this. Don't say it. How can we show that 1 and 3 are congruent? We got a 2 up there also. What do you think? Can I relate 2 and 1? Yes, sir.
1 and 2 are opposite angles, so they're congruent.
Ah, okay. We know that we've got this, very good. We've got this parallelogram up here, right? And they're opposite angles in that parallelogram, so they must be congruent. Good. So we can add that in. Tim.
1 and 3 corresponding?
1 and 3, I don't see how they could be, but are 2 and 3 related?
2 and 3 are the same thing. They're equal.
Okay, good. So in the other parallelogram, 2 and 3 are opposite angles, so they must be congruent. Now, if 1 and 2 are congruent, and 3 and 2 are congruent, somebody raise your hand. What's the property that would tell me that 1 and 3 are also congruent? See if you can think of it. I know it's on the list, so you can always look at the list. But does anybody remember? What do you think?
Transitive.
Transitive. Very good. Okay, so yeah, there's our proof. Okay, we know that 1's congruent to 2, 2's congruent to 3. Like we said, opposite angles in a parallelogram are congruent. Then the transitive property would tell me that 1 has to be congruent to 3. Very good. Okay. All right, so what else? Let's maybe look at one more of these. Okay, say we want to prove theorem. 6.2, I guess, is the one where if we're given a parallelogram, we're supposed to prove that AB opposite sides are congruent. Pairs of opposite sides are congruent. Okay. Now let's maybe walk through this one a little bit. What we got to do in a situation like this, there's not very much to go on. If all we're given is that it's a parallelogram, there's not much there. But we could turn this into triangles. We have a ton of information about triangles. So in addition to the thing that we're initially given, we're able to say something like, let's go ahead and connect points B and D. Let's add the diagonal BD. So then that would be given to us also, because we've just constructed it. That's no big deal. We can create a segment. Now, does that help us? If we know that A, B, C, D is a parallelogram, somebody raise your hand and give us something we got going here. Okay, there's one thing we know. We have the reflexive property of congruence, so let's draw that in. Okay, so there's one thing. Now, somebody else, something else. Something else. That's good. We got reflexive property, so that gives us some sides. Oh, hang on. Somebody else. Yes, sir.
Opposite angles.
Which ones are you looking at?
I don't know. Opposite angles.
Opposite angles.
A and C, sure, because we have a parallelogram. So we got A and C, that's good. Okay. What else? Anything else we know there?
Opposite sides of the triangle.
Okay, good. By the definition of a parallelogram, we know that the opposite sides are parallel. Okay, so now Look at that. We got to get, in order for us to show that opposite sides are congruent, can you think of sort of an overarching strategy here? What's our goal? How are we going to involve these triangles in that proof? Raise your hand. Give me an idea how can we do that? Let's not get specific. If we can somehow show, we're not quite there yet, but if we can show that the top triangle is congruent to the bottom triangle, is there a way that we could show then that side AB is congruent to side CD, for example? Say it again. Oh, probably. There is. What's that step we have that if we can show triangles are congruent, then the corresponding pieces of those triangles? Oh, I heard it. CPCTC. Corresponding parts of congruent triangles are congruent. That's a good strategy. If we can show the triangles are congruent, if we can show that triangle ABD is congruent to triangle CDB, then those would be, this guy and this guy would be opposite, would be corresponding parts of those triangles, and so they would have to be congruent. And we got our proof, right? That's what we're trying to show in this proof. So all we need then is just to somehow show that those triangles are congruent. Okay, maybe. Somebody, so we got it. That's the last thing we need. We need one more piece of these triangles. I'm going to give you a hint. No one should raise your hand. Don't say anything out loud. What if we do this? What if we extend those sides? Now, don't say anything, please. I want everybody to get a chance at this. I know you know it, right? Let's see somebody else get. That, if I extend those, what's that look like? Parallel lines cut by a transversal, right? So do we see some angles there that are congruent that might be important? ABD, there you go. ABD could be congruent to CDB or BDC. There you go. Good. Okay, now, is that enough? If I pull these triangles apart, which is useful to do, right? And at least imagine it. I've got this triangle up here and this triangle down here. Is there a triangle congruence relationship here that would apply? Okay, well, AAS we call it, right? Angle, side, right? Congruent to angle, sides. Everybody see that? Okay, so yeah, we got it then. By angle, side, we know that the top triangle is congruent to the bottom triangle. And so now we know all the corresponding parts are congruent, and that's all we need for our proof. That's a pretty good one. That's kind of a longer proof. So let's look at it. Right? So we had definition of a parallelogram, good. The opposite sides are congruent. We had alternate interior angles would give me, we don't need all these, but we could do more if we wanted to. But I've got those two, for example, right? And they added more congruences than we did here, but we actually, frankly, probably did this a little easier than they did. We didn't use angle, side, angle. We used angle, side. But ultimate result was the same. Then we're able to say that, okay, we know that segment AB or side AB is congruent to side CD by CPCTC, and we could also say that AB and, AD and CB are congruent, same reason, right? They're corresponding parts of those triangles that we just proved congruent. That's good stuff. Okay? All right, that's a little more advanced proof. I like that. Whoops, I guess we're done with that guy. Okay, so that's 6.2. Now, in 6.3, I want to make an analogy here. If you know 6.2, you know 6.3. Because remember how when we dealt with, way back in, I guess it was chapter 2. I can't remember what chapter it was. But when we dealt with the parallel lines transversal stuff, right? Chapter 2. We did all those theorems. We did like alternate interior angle theorem. We did or alternate interior angle postulate. Or no, corresponding angle postulate, alternate interior angle theorem. We didn't care if they're theorems or postulates. Alternate exterior angle. We had all those, right? And then we went to the next section, and all those came from the fact, in that first section we said, if parallel lines are cut by a transversal, then you have all these angle relationships, right? The next section we said, let's turn those around and do the converses. If we know that if you have two lines, we don't know if they're necessarily parallel, but if we have two lines that are cut by a transversal, and we can show that those relationships are true, then the lines must be parallel, right? So we did the converse of each of those. Same thing that's the same relationship we're looking at here. In section 6.2, we said if we've got a parallelogram, then we get a bunch of these relationships, right? 6.3, we're saying we can prove that a quadrilateral is a parallelogram if those relationships exist. We're just turning the theorems around, doing the converses all, right? So we end up with stuff like this. So if we've got some quadrilateral with two pairs of opposite congruent sides, it's got to be a parallelogram, right? That's a property that we just talked about of a parallelogram. If we've got a quadrilateral where both pairs of opposite angles are congruent, parallelogram. That's a property of parallelograms also. If we got a quadrilateral where consecutive angles are supplementary, then, you guessed it, parallelogram. If we've got a quadrilateral where diagonals bisect each other, it's a parallelogram. Okay, so those are things that we can use in proofs to prove a parallelogram. Let's look at, I'm only going to look at one of these proofs. Let's look at this guy. See if we can come up with a way to prove here. What are we trying to prove? We're trying to prove that 6.6, which one is that? That's, prove it's a parallelogram, duh. Right. Okay, so if we know that opposite sides are congruent like this, can we prove it's a parallelogram? Well, the same trick as before. Let's go ahead and draw in line AC, segment AC, diagonal AC. And then we know, okay, there's one thing we know too. Good, we know that that's congruent to itself, right?
And we already know that BAC and DCA are congruent.
Okay, so now we know by what, don't say anything, by what triangle postulate or what triangle relationship do we know that those two triangles are congruent?
Side, side,
Side, side, side. Yeah, right? So that's helpful. So we know side, side, side congruence postulate.
Everything else in by CPCTC.
And so we could put the other stuff in if we want to. Sure. Right? We could add the angles.
Oh.
So those are congruent, right? So we know those are congruent. For example, we'd know that those are congruent. And we'd know those are congruent because those are corresponding parts, right? Okay? And we got a lot now. We're trying to show this as a parallelogram. Well, if those angles are all congruent, now we're going to go back to chapter 2 again for a second, right? Now I want you guys to just think about this for a second. Don't say anything yet. So there's, if I extend those lines and I extend those lines, so I've got now two lines cut by a transversal, right? And I've got all those angle relationships existing. Can I show that those are parallel lines? Because that's my goal, isn't it? If I want to show this as a parallelogram, I'm trying to prove this theorem, right? To show it's a parallelogram. Well, the definition of a parallelogram is what? Well,
I know what it is.
the definition of a definition, not the theorems, not the properties of, but the definition of a parallelogram is, yeah, two pairs of opposite parallel sides. So if we can show that these lines are parallel and those lines are parallel, let's just do one of them, and then by analogy, the other one will be the same
We
way.
already know if the two sides are parallel. The
Well,
lines
We don't know they're parallel yet. We don't know they're parallel
They're
yet.
the same length and they're the same angle. You already know that.
Okay, but that's the theorem that we're proving. You see what I'm saying? So we can't use that theorem to prove itself. But we can show those lines are parallel with this angle information. Now, nobody say anything yet. Just look at this, though, for a second. I've got two lines cut by a transversal. Let's just focus on, say, these guys right here. What kinds of angles are those? That guy and that guy. What are those? Alternate interiors. Now, we've got a theorem that says if two lines are cut by a transversal so that alternate interior angles are congruent, what's the result? The lines are parallel. And that was just our alternate interior angle converse, right? Okay? So there we go. We got it. So we know by the alternate interior angle converse, we could show that those lines are parallel, or we could have extended those lines, right? Instead, same thing would have applied. And so then by definition of a parallelogram, if those lines are parallel and those lines are parallel, we got it, right? Good. Good stuff. Oops. Okay, so with this, forget that, I don't know how this is supposed to be a sewing box, but in this example, does it make sense that this thing has to be a parallelogram then?
Yeah.
How come? Yeah, good, because I get two pairs of opposite congruent sides. We just proved that. That works.
Maybe the boards were more.
Maybe. Okay, another theorem we get then. Now this is something else we can add. We get an extra one. Get an extra one when we're proving parallelograms. If two pairs of sides in a quadrilateral, so just this, one pair of opposite sides are both parallel and congruent, that's actually enough. That's enough for us to know this is a parallelogram. Even if I don't know anything about sides A, B, and C, D, if I know that side BC is both parallel to and congruent to side AD, that's enough. I got it. Okay, and then there's we won't go through another proof. We'll look at that later, maybe. I'll do it in a different period and I'll record it. So if you want to see it, you can look there. Excuse me. Okay, so coordinate geometry, real quick. Coordinate geometry just means that if we put these shapes in the xy plane and we know the coordinates of the vertices, a lot of times we can make calculations of things like slope and length of segments to show that shapes are parallelograms, or later on rhombuses and squares and things like that. So for example, if I'm given the coordinates of quadrilateral ABCD, how could I show that it's a parallelogram? There's a bunch of ways I could do it. What's one way I could do it? If I know the coordinates of each of those vertices. Yes, Maddie? I could find the slopes, sure. I could find the slope of line CB and the slope of line AD, and what would have to be the case for this to be a parallelogram? Those would be the same, and also, if I found the slopes of the red lines and they were the same, I proved it. That's one way to do it. What's another way? I could do it by slopes. What else? Say it again. I probably could. I could do a normal proof, but what if I just want to use properties of those coordinates? Like I know where the coordinates are. So could I, for example, find the length of that segment? How would I do that? Distance formula. I could use the distance formula to find the length of that segment. How could I use that to show this is a parallelogram? If I found the length of BC, what else would I have to do? Find the length of AD, and if they're the same number, right, then they're congruent. And then do the same thing for BA and CD, right? Okay, so if I just look, if we were to do that, whoops, and you guys will get plenty of chances to do this, I would find. Now, if I wanted to calculate, let's just look at one of these, and I won't drag you through all of them, but if we just review this real quickly, if I want to find the slope of, say, AB, well, the coordinates, you may not be able to see this. Let me make these a little bigger. Point A has coordinates 2, -1. Point B has coordinates 1, 3. So I'm just going to use the slope formula, right? Rise over run. The slope would just be, the slope of AB would just be, you tell me. How would I find the slope between those 2 points?
Take y2 plus y, or y1.
Okay, y2 minus y1. Y2 minus y1 over. Okay, so that's just going to look like -1 minus 3, or 3 minus -1. But I have to just, if I'm going to pick this one to be y2, that's got to be x2, right?
It's gonna end up being 4
Either way. And then I'm going to get, now I subtracted 3 from -1, so I've got to subtract 1 from 2. So I'm just going to get, what? -4 over 1 is -4. Right? And if I calculate the slope of CD, notice that I get the same thing. So those are parallel, right? Slope of BC, if I calculate the slope of BC, 5 minus 3 over 6 minus 1 is 2/5. Okay? If I calculate the slope of AD, 1 minus -1 is 2 over 7 minus 2 is, they got that backwards. Oh, they did it the other way. That's fine. They did -1 minus 1 is -2 over 2 minus 7 is -5. Negative over negative is positive. Either way, it's going to work. 2/5 and 2/5. To me, slope's a lot easier to work with than distance formula. If I'm proving a parallelogram, I'm going to use slope. But either way, I could also do it with distance formula. Let's look at just one of these. If I want to find the length of AB, remember the distance formula, right? Distance equals, how did I do that? What's the distance formula? Square root of
x1 minus x2 squared.
well, let's make x2 minus x1 squared plus
y2 minus y1 squared.
Right. Good. So if we plug that stuff in, let's see, from A to B, we're going to say that the difference in the x's, so 2 minus 1 would be x2 minus x1. Or they did it backwards. They did 1 minus, same thing. 1 minus 2. Difference in the y's then would be 3 minus -1. Okay. 1 minus 2 is -1, but when I square a negative, what do I do? Square the positive. So 1 squared is 1. And then 3 minus -1 is 4. 4 squared is 16. So 1 squared plus 4 squared is 1 plus 16 squared is 17. Do I need to make it any simpler than that? No. Just leave it as square root of 17. If I get square root of 17 from the other side, when I do the distance formula, which I do, then I know that they're congruent. Right? I can do the same thing, so those are congruent. If I did the same thing for the blue segments, I'd get square root of 29 for both of them. So I just showed it, right? I just showed that those sides are congruent and those sides are congruent. So that's parallelogram. Okay? So that's when we talk about using coordinate geometry. That's the fancy name for that, you know. So you know the coordinates, so you can use distance formula and slopes. All right, so, well, we've seen enough of that stuff. Okay, last, what are we at here? 50? 50, okay. How many of you guys are close to being done with 6-2? Or done or close to being done? Okay, how many people have gotten a pretty good start on 6-3? Okay, all right. So tomorrow we'll try to get in the lab. See, I hope we can get one of you, and you can maybe kind of wrap that up a little bit. Okay, 6-4. I want to just give you, just for some of you, we'll come back and look at this some more.